have been discussing stationary perturbation theory, and in the last lecture I have been looking at the degenerate case. So just by way of recapitulation, some salient features and the terminology, let me put down the notation again. And this is stationary perturbation theory. The total Hamiltonian H is H naught plus H prime. The example that we select is where H prime is a constant electric field along the z-axis, and we work in the dipole approximation. Therefore, H prime is minus d dot E, where d is the atomic dipole operator, and indeed we have been looking at the hydrogen atom problem. So the problem considered is hydrogen atom. And the states that we consider correspond to n equals 2, and therefore there are 4 states, all of them with the same energy value. The dipole operator itself is minus ER, and this electric field is modulus of E times Ez, because I have selected a constant electric field along the z-axis, and therefore H prime is simply E Z, because it is only the Z component of R that is going to give a contribution here. Notice that Z is R cos theta, if you want to write it in spherical polar coordinates, which indeed is what I would do, because in this problem a typical wave function of the hydrogen atom is given by specifying 3 quantum numbers n, L and m. So for a given n, and we have chosen n equals 2, L takes values 0 to n minus 1, and for a given L, m takes values plus L to minus L in steps of 1. So these are the 3 quantum numbers. Then of course I will recall for you a couple of expressions that we derived. We had this expression for the first order contribution to the energy. So if you are talking about the discrete level n, I could use the same n here and here, because E sub n depends upon the value of n. So En1 is simply psi n0 H prime psi n0. And what psi n0? They are the eigenstates of the unperturbed Hamiltonian with corresponding eigenvalues En0. So the first order contribution to the energy, or the correction to the energy once we put in the perturbation and only worry about the first order term in the perturbation, is this. The corresponding contribution to the wave function, I call that psi n1, is summation over all k not equal to n, psi k0 H prime psi n0, that is a number, so there is a ket here, psi k0, divided by En0 minus Ek0. And to quickly recapitulate what we had, problem arises when there is a degeneracy, because then the denominator becomes 0, and that is okay provided the numerator becomes 0. And we are only interested in all k not equal to n. So now let us return to the problem of the hydrogen atom. What are the states that are involved? You've selected n equals 2. In fact, there are 4 states: psi 2 0 0, psi 2 1 0, psi 2 1 1, and psi 2 1 minus 1. This is n, that is L, and that is m. And remember that L takes values 0 to n minus 1. So, that is 0 to n minus 1. And for a given L, m takes values minus L to plus L in steps of 1. So, we have these 4 states. Now, what is the first order contribution to the energy in these states? So, what is E1? For instance, if you take the state psi 2 0 0, I need to compute this object. Now, H prime is essentially of the form D dot E, and we have selected the electric field to be along the z axis. So, really this gives me a z, and that is some E naught. Look at this. Electromagnetic interactions and strong interactions conserve parity. Now, what does that mean? If you look at the parity of this state, this is minus 1 to the L, and L is 0, which is plus 1. When you say that electromagnetism conserves parity, it means that the parity operator commutes with the Hamiltonian. So, look at this. The net state, the net matrix element of the Hamiltonian, if you take it, here there is a z, and under parity that changes sign. So, you pick up a minus 1 here, and that is a plus 1, but the net parity must be plus 1 because of this, and therefore, this state, whatever I put here in the bra, should have odd parity because that had even parity. So, there is no way I can use a psi 2 0 0 here, because if I did that, this has parity plus 1, that has parity plus 1, that makes it even parity, but you see there is a contribution here to parity which is minus 1, and parity is a multiplicative quantum number, and therefore, this contribution is 0. Now, I will use the same argument to show that the contribution psi 2 1 0 H prime psi 2 1 0, this matrix element is also 0, same argument. Here the parity is minus 1 to the 1, and here too minus 1 to the 1, but this provides another minus 1, and therefore, the net parity is minus 1, which is not on. How do I get out of this problem? So, if you want to lift the degeneracy and in the first order produce different contributions to the energy of these states, we try to use a superposition. In other words, we construct new states. For instance, I could construct a state phi 1 0, which is a linear combination of all these states. Now, if I did this and I say I work with this and suitable combinations of this kind, the relevant contribution to energy to the first order would really be this object, and so on. I would construct a phi 2 0, which is another superposition, a phi 3 0, which is another superposition, and a phi 4 0. And here I would expect that the contribution would be non-vanishing, because clearly there will be terms of this form. such a contribution would in general be non-vanishing, because this is parity minus 1 to the 1, it's minus 1, and that again produces another minus 1. So the total parity there is plus 1, which matches with the parity here, which is minus 1 to the 0. And since such matrix elements do not vanish, I would imagine that the first order contribution to the energy would be different for different superpositions, thus lifting the degeneracy. But what are these contributions? I can only include such contributions where the matrix element of the Hamiltonian between the unperturbed states is non-vanishing. But you consider a thing like this. Consider psi 2 1 1 H prime psi 2 0 0. This contribution is 0, because if you look at the angular integration, H prime has a z in it, which is r cos theta. Apart from the magnitude of the electric field, the electric charge, and so on, it has a z, which is r cos theta. And then this angular integral would be a y11 of theta phi from there, a y00 of theta phi from here. These are all real functions of theta and phi, so I don't put a star, times a z, which gives me a cos theta, and then the angular integration sin theta d theta. I am not looking at the phi integration. Now y00 is merely a number, it is a constant, so I can remove that, and y11 of theta phi is proportional to sin theta. So this is essentially integral sin squared theta cos theta d theta, and that vanishes because theta goes from 0 to pi. Substitute sin theta as u, and therefore I have a u squared du. When I integrate, I get a u cubed by 3, where u is sin theta, and therefore such terms do not contribute. Similarly, this is by explicit calculation. Integration over theta. Similarly, if you look at psi 2 1 minus 1 H prime psi 2 0 0, that is also 0, explicit integration. Now if you look at psi 2 1 0 H prime psi 2 0 0, parity is conserved, because this has got even parity, that has odd parity, the combination has odd parity, and this has odd parity. But if you look at this term, this, if you look at the theta integration, you would just have the following. You would have integral y10 of theta phi cos theta from H prime, because there was a z which was r cos theta, y00, which is a constant, sin theta d theta, and this y10 of theta phi is actually proportional to cos theta, and therefore this integration from 0 to pi is not equal to 0. So the only terms that would contribute in a superposition like this, that would make intelligent contributions, non-zero contributions, would come from matrix elements of H prime with the state psi 2 0 0 here and psi 2 1 0 there, or vice versa. And therefore there is no point in producing superpositions which include psi 2 1 minus 1 and psi 2 1 1. If you consider the contribution of this type, this is also 0 by parity arguments. Hence the only non-vanishing contribution comes from this in this specific example, and therefore I define phi 1 0 is some S11 psi 2 0 0 plus S21 psi 2 1 0, and I define another combination phi 2 0 is S12 psi 2 0 0 plus S22 psi 2 1 0. So, what do I have for the initial states now? I have the following. I have phi 1 0, phi 2 0 instead of psi 2 0 0 and psi 2 1 0. I have made these superpositions, and then of course I have psi 2 1 1 and psi 2 1 minus 1. These are my 4 states. Now, this superposition will hopefully lift the degeneracy between 2 of these states. There was a 4-fold degeneracy, and what about the other 2 states? They continue to have the problem, and one has to go to a higher order in the perturbation theory in order to lift the degeneracy between psi 2 1 1 and psi 2 1 minus 1. So, for the moment we will only worry about the mechanism that lifts the degeneracy in this sector, the sector which involves psi 2 0 0 and psi 2 1 0. So, what do we have here? Remember that when we derived the expressions for contributions to first order, we showed that H naught minus E n 0 psi n 1 was E n 1 minus H prime psi n 0. In fact, this was our starting point for first order perturbation theory. So, in this case I would have H naught. Let us first look at what we get when H naught acts on phi 1 0. That is the same as E 1 0 phi 1 0, but there is a degeneracy, and therefore H naught acting on phi 2 0, which would normally be some E 2 0 phi 2 0. E 1 0 and E 2 0 are the same, and I am going to represent them as E 0. So, in this case I merely have H naught minus E 0 phi 1 1, that is the first order contribution to the state phi 1, where the 0th order contribution was written like this. That is E 1 1 minus H prime phi 1 0. That is my first equation. Then my second equation is H naught minus the same E 0, because there was a degeneracy, phi 2 1 is E 2 1, the first order contribution, minus H prime phi 2 0. These are the 2 equations that I should be dealing with. So, I am really working in a 2-dimensional subspace of the original space. A crucial input would be this: what would be the first order contribution to the wave function? Well, we are not going to worry about psi 2 1 1 and psi 2 1 minus 1 anymore. We are merely going to look at the 2-dimensional subspace. So, phi 1 1 would be, there are exactly 2 states, phi 1 1 and phi 2 1. So, this would just be phi 2 0 H prime phi 1 0 times phi 2 0 by E 0 minus E 0 in my notation. And since the denominator goes to 0, I would want the numerator to also go to 0 in order to get a non-zero value, a finite non-zero value. Similarly, if I look at phi 2 1, I would have a phi 1 0 here, a phi 2 0 there, and a phi 1 0 here. So essentially, one has this requirement that this matrix element becomes 0 because the denominator blows up, and I would expect the numerator also to go to 0 in order to extract a non-zero finite contribution to the wave function in the first order. So let me look at these equations. So I have H naught minus E 0 S 1 1 psi 2 0 0 plus S 2 1 psi 2 1 1 1 0. That is what I have here. That is E 1 1 minus H prime, S 1 1 psi 2, I have phi 1 1, right. So let me start with phi 1 1. This is S 1 1 psi 2 0 0 plus S 2 1 psi 2 1 0. This is my first equation. Let me do the following. Let me flank it on this side with psi 2 0 0. What do I get? I have the following expression. This is what I have. That gives me an E 0 psi 2 0 0, and therefore the E naught cancels out, the left hand side is 0. Look at the right hand side. The first term is E 1 1, and remember psi 2 0 0 is orthogonal to psi 2 1 0. So the contribution is really E 1 1 S 1 1, which is just a number, minus psi 2 0 0 H prime. H prime cannot connect states of the same parity, so I can only work with psi 2 1 0 on this side, and there is a coefficient S 2 1. So that is the first equation that I have. In other words, I can well write it as follows. S 2 1, and then this matrix element H prime sandwiched between psi 2 0 0 and psi 2 1 0 is E 1 1 S 1 1. So that is the first equation I have. Now instead of working with psi 2 0 0, let me work with psi 2 1 0. Now if I did that, let me start with psi 2 1 0. This step continues because H naught on psi 2 1 0 is E naught. To 0th order, these are degenerate states. They have the same energy value, and therefore the left hand side is 0. Now, as far as the right hand side is concerned, I have E 1 1. H prime connects states of opposite parity, so the contribution will come from S 1 1 psi 2 0 0 and not from S 2 1 psi 2 1 0. Therefore, I have E 1 1 times S 2 1. This state is orthogonal to that state, but not to this, minus psi 2 1 0 H prime psi 2 0 0, and there is an S11 out there. So, I will write it as minus S11. This is the right hand side, which tells me that S11 psi 2 1 0 H prime psi 2 0 0 is E11 S21. That is my second equation. To remind you, I started with this equation and I flanked it with bra psi 2 0 0 first and got this equation, then with bra psi 2 1 0 and got this equation. What does that tell me? It tells me that if I wrote this as an eigenvalue equation, I have 0 psi 2 0 0 H prime psi 2 1 0, psi 2 1 0 H prime psi 2 0 0 here, and 0. These are the matrix elements. There is 0 and then this matrix element. This is the complex conjugate of that, but we are dealing with real functions. So, if I compute this matrix element, that is the same as this, and there is a 0, I have an eigenvalue equation. The job is to solve this. First, explicitly evaluate this matrix element, solve for the eigenvalue and the corresponding eigenvectors, which means I get S11 and S21, and therefore I have phi 1 0. So, that is the first of the equations. Now, let us look at the matrix element. So, if you wish to compute psi 2 1 0 H prime psi 2 0 0, have to feed in everything now. The expressions are here. Psi 2 0 0 has a y 0 0, and then there is an r dependence, r 2 0 of r, RNL of r, and that is out here. Notice the exponential fall off e to the minus r by 2 a 0, where a 0 is simply h cross squared by mu e squared, mu being the reduced mass. These are expressions that we derived when we looked at the hydrogen atom problem. After all, these are the unperturbed wave functions for the hydrogen atom. Now, if you look at psi 2 1 0, apart from the radial dependence, which is different from this, but which certainly has that exponential fall off to match boundary conditions, there is a cos theta, because y 1 0 is proportional to cos theta. Now, these two have to be substituted in calculating this matrix element, and for H prime we have an electric field whose magnitude is given to us and a z which is r cos theta. This integration has to be done. The integral over r goes from 0 to infinity, theta 0 to pi and phi 0 to 2 pi. I leave it to you as an exercise to show that this is minus 3 e e a 0, where e is the magnitude of vector E. Remember, that was a constant electric field in the z direction. So, I can now go back and write down that equation. The eigenvalue equation is therefore 0 minus 3 e e a naught minus 3 e e a naught 0 S11 S21 is E11 S11 S21. What is it that we are trying to do? We are diagonalizing the perturbing Hamiltonian in the superposed basis. So, we are using components S11 and S21 and working in that basis. So, now the eigenvalues can be got. You will get a quadratic, because this implies that E11, determinant of this object, in order to get the eigenvalues, and therefore the eigenvalue, the contribution to first order is plus or minus 3 A0. Now suppose I had worked not with this, but with the other equation, the equation for phi 2, what would I have got? To complete this story, before we get there, I can now substitute this eigenvalue and find out S11 and S21, and it turns out it's a trivial matter to show that S11 equals S21 is 1 by root 2, and therefore I have this normalized state phi 10 is 1 by root 2 psi 2 0 0 plus psi 2 1 0. And therefore I have found out the energy eigenvalues, could be plus or minus, but remember that there is an E21 as well. So let's see what that gives us. Should give us pretty much the same thing, because if you now go back and redo the calculation, you will have the following equation: H naught minus E naught on phi 2 1 is E21 minus H prime phi 2 0, and phi 2 0 in terms of the unperturbed basis was this. Once more, I can flank it with psi 2 0 0 to begin with. So let's redo this. Psi 2 0 0, H naught minus E naught phi 2 1 is psi 2 0 0, E21 minus H prime S12 psi 2 0 0 plus S22 psi 2 1 0. It's evident that in this case, the corresponding eigenvalue equation would be used to determine S12 and S22, and therefore phi 2 0. This is phi 2 0. Once more, the left hand side is 0, because H naught, because psi 2 0 0 is an eigenstate of H naught with eigenvalue E naught. So the left hand side is 0, and the right hand side gives me 0 is E21. What is the non-vanishing element here? It's S12, because psi 2 0 0 is orthogonal to psi 2 1 0. So I have S12 minus, use the fact that H prime only connects states of opposite parity. So I have S22 psi 2 0 0, H prime psi 2 1 0. So I have the first of my equations. S22 psi 2 0 0, H prime psi 2 1 0. Remember, this was minus 3E magnitude of the electric field times A naught. This quantity is E21 S12. So that's the first of my equations. Instead, I now work with bra psi 2 1 0 as before. The left hand side is 0. As far as the right hand side is concerned, I have an E21, and the non-vanishing contribution comes from here. That's an S22 minus psi 2 1 0 H prime psi 2 0 0 with an S12. So this is what I have, and therefore I have S12 psi2 1 0 H prime psi2 0 0 Z21 S22. Same thing as before, it's the real matrix element. Diagonalize this matrix and you will retrieve E21 is plus or minus 3 E A0. You will also get S12 equals minus S22 equals 1 by root 2. The degeneracy is obviously lifted because I have E11 is say minus 3 E A0 and E21 is plus 3 E A0. I also have the orthogonal states phi 1 0 and phi 2 0 because phi 1 0 was 1 by root 2 psi 2 0 0 plus psi 2 1 0. That is what I had, and I have phi 2 0 is 1 by root 2. Remember, there is a relative negative sign here. Psi 2 0 0 minus psi 2 1 0. This is what I have. The corresponding energies, therefore, to first order, the energy E1 is E0, which was common to both states, minus 3 E A0, and E2 was E0, which was common to both states, plus 3 E A0. And as to the wave functions, phi 1 is phi 1 0 plus contribution from first order, and phi 2 is phi 2 0 plus contribution from first order, and that is a simple matter to settle. Remember that in the original notation, the first order contribution to the state psi n is summation k not equal to n psi k 0 h prime psi n 0 times psi k 0 with the denominator E n 0 minus E k 0. And therefore, we now have phi 1 is phi 1 0, and we know what is phi 1 0. That was this superposition of the unperturbed states plus phi 2 0 h prime phi 1 0 by a denominator which was just E 0 minus E 0 phi 2 0. The only thing we need to check out is that this matrix element is 0, which indeed it is, because if you feed in phi 2 0 is 1 by root 2 psi 2 0 0 minus of this, and phi 1 0 is 1 by root 2 psi 2 0 plus this, it will be evident that in the superposition the only contribution will be from psi 2 0 0 here and psi 1 0 0 there, psi 2 1 0 there, or vice versa. You will simply get a 1 by root 2 times 1 by root 2 for the first term and a 1 by root 2 times minus 1 by root 2 for the second, and therefore the numerator is 0. And this is all that I have. The numerator is 0, the denominator is 0, I can get a sensible expression out of this, and I have the first order contribution. I also realize that to first order the degeneracy has been lifted between these two states. The other two states continue to be degenerate. The states psi 2 1 1 and psi 2 1 minus 1 are degenerate even in first order. So, as I indicated earlier, one goes to higher order perturbation theory to lift that degeneracy. What you have seen is called the linear Stark effect. This is the Stark effect, where you use an electric field to lift the degeneracy between two of the hydrogen atom states corresponding to n equals 2. That is the first excited state. Linear because it is proportional linearly. E appears not as a quadratic, but as a linear object to power 1 in E, and therefore it is called the linear Stark effect. There is a counterpart to this, which is the Zeeman effect. Instead of using an electric field to lift the degeneracy, you could have used a magnetic field, a uniform magnetic field, to lift the degeneracy. So, let us look at that. So, that is the next example of degenerate perturbation theory. There are certain striking differences between using a magnetic field and an electric field. So, let me look at the Zeeman effect. Once more I have the same states, psi 2 0 0, psi 2 1 0, psi 2 1 1 and psi 2 1 minus 1. And I now consider the electron with momentum p. The free Hamiltonian, of course, is p squared by 2 m, but let us be careful about the notation. This is n, that is L, and that is m, the quantum number. So, what I want here is really the we are looking at the hydrogen atom problem. So, this would be the reduced mass. So, mu is the reduced mass. So, I write h as p squared by 2 mu, and now I couple it to a magnetic field. So, that means that p goes to p minus E A by C, and therefore, the Hamiltonian itself is p minus E A by C dotted with p minus E A by C, and the whole thing has a 1 by 2 mu outside. So, what are the various terms? This is my new Hamiltonian. This has the old Hamiltonian p squared by 2 mu as the first term. Then I have plus E squared by 2 mu c squared A squared. That comes from here. Obviously, there is no interaction between there is no term which involves p dot a or a dot p here. However, there is a cross term coming up now, and that is plus 1 by 2 mu or minus 1 by 2 mu. So, this quantity is expanded out here, minus 1 by 2 mu E by C A dot p. So, let us also put the E by C outside, A dot p, that is from here, and this gives me an E by C p dot A, and A dot p is not the same as p dot A, we have to be careful. Look at H prime, it is minus E by 2 mu C A dot p plus p dot A. The magnetic field B itself is del cross A. came about because del dot B is 0. I use a uniform magnetic field, say along the z-axis, and therefore delta B by delta Z equals 0, delta B by delta X equals 0, and so on. And therefore, I can write A as half B cross R. We will use this later, but look at P dot A. Consider P dot A. That is minus IH cross, say P dot A psi is minus IH cross del dot A psi, and that is minus IH cross del dot A psi minus IH cross A dot grad psi. That is what I get. This thing with A being given by half B cross R, del dot A becomes 0. And this object is simply A dot P psi, and therefore, what is left of P dot A, what I need to use is simply A dot P. The contribution from here is simply A dot P, and therefore, H prime simplifies and we have the following expression for H prime. Minus E by mu C, where mu is a reduced mass, A dot P. That is all. So, this is the perturbing Hamiltonian. Now, what happens? How do I find the energy eigenvalues? To begin with, I know that these states and psi 2 1 1 are degenerate, because the energy simply depends upon the n value. The idea is to use the fact that their L and M values are different and see what we can get. So, let me substitute for A. So, it is minus E by mu C. A is a half B cross R dot P. I can just write this as B dot R cross P. But B is along the Z axis. I have chosen a uniform magnetic field along the Z axis with magnitude B, and therefore, that is minus E by 2 mu C magnitude B Lz, because I need to worry about the Z component of the orbital angular momentum. It is clear that I have not put in spin. So, this is I am trying to address this problem with just the orbital angular momentum put in, excluding spin for the moment, and seeing what exactly I get. So, this is the operator that I have. This is H prime. This is H prime. I do not need to consider superpositions anymore, because if you look at the expectation value of H prime in any one of these states, it amounts to Lz acting on these states and pulling out an eigenvalue. These are eigenstates of Lz with eigenvalue mh cross. So, it is pretty clear what is going to happen. There is no need to consider superpositions. Let us look at the contribution to energy. So, E1, the first order contribution, In one case is psi 2 0 0 H prime psi 2 0 0, and what is that? That is minus E by 2 mu c. I can write an EH cross and put an H cross there, because EH cross by 2 mu c is the Bohr magneton. Expectation value of Lz in the state. So that is minus the Bohr magneton, let me call that mu b by H cross b. Expectation value of Lz in this state is 0. Remember, Lz acting on psi 2 0 0 is 0 H cross psi 2 0 0. So the answer is 0. Now if I consider psi 2 1 0 H prime psi 2 1 0, by a similar token I get minus mu b by H cross times 0, because the m value is 0. And therefore, there still continues a degeneracy between psi 2 0 0 and psi 2 1 0, even in the first order, analogous to the linear Stark effect. But in contrast to the case of the electric field, the Stark effect case, I do not need superpositions. I work with the original states, but I can see that I cannot lift the degeneracy fully. On the other hand, this is certainly true. If I look at the first order contribution psi 2 1 1 H prime psi 2 1 1, this is minus mu b b. Let us forget that H cross, because Lz pulls out an mH cross and the H cross will cancel out, times 1, that is the m value. And if I look at psi 2 1 minus 1 H prime psi 2 1 minus 1, that is mu b b. So this is what I have. Normally I should have written it as minus mu b b m, that is the energy, the first order contribution. But as you can see, the degeneracy between psi 2 1 1 and psi 2 1 minus 1 have been lifted, in contrast to the case of the Stark effect, where the degeneracy between psi 2 0 0 and psi 2 1 0 was lifted. So here I now have two states, psi 2 0 0 and psi 2 1 0, with energy 0, and then I have two states, one of them with energy mu b b and the other with energy minus mu b b. So one of them is psi 2 1 1 and the other is psi 2 1 minus 1. So the other two states, not the ones where the degeneracy was lifted in the case of the constant electric field, but the other two states, their degeneracy has been lifted, whereas these states continue to be degenerate, and this is called the Zeeman effect. You have to go to higher orders to lift the degeneracy between psi 2 0 0 and psi 2 1 0. So these are two examples of degenerate perturbation theory. Essentially, in the first example that I worked out for you, I showed you how superposing states helped, and you could lift the degeneracy at least partially, that is in a subspace, in the first order of perturbation, whereas in the Zeeman effect there was no point doing a superposing. On the other hand, the fact that these were eigenstates of Lz helped us lift the degeneracy, again only partially, because we used an external magnetic field. In general, in a more complicated example, you might have to superpose more states and work in a higher dimensional space to remove the degeneracy. To that extent, you will have to diagonalize a bigger matrix and see what you get to first order in the perturbation theory.